Okay. So I got a little late of a start this morning. I wasted a bunch of time this morning. Let's just be honest. So 5:45. We'll go to maybe 1 p.m. I think that'll be sufficient for the session. Probably just gonna watch a lecture or something. Save that bad boy. Bam. My lunch and cardio will come there. Yes. Just that event. Afternoon stream. Let's see. This is gonna be a 2-hour. Yeah, I'll do that. So this will end at 5. Okay. That's the plan for the day. Unfortunately, I wasted over an hour and a half this morning. Hour and 3/4. Just time wasted. Brown. Save. Yeah, it's not good. Definitely not good. Definitely not good. Tomorrow I have an early morning stream. But then I have D&D. So really the weekends are really the times when I have like 4 slots. During the week it's hard for me to get more than 3 slots a day, 3 streams in. Alright. So let's go for 2 hours here. I'll leave that going, kill that, go over here, and we're going to jump to CSAPP, get status, then readme, and interesting. Alright. So we have our labs, we have a recitation for the shell lab. You can read the handout for the shell lab, or you continue watching the lectures. Let's finish the system of IO lecture. I think that probably would be good use of time. So I was watching this during my downtime.
Everyone.
Already, I got pretty far in it.
Where it's gone through, what layers in the protocols it's gone through, but 1,500 bytes is actually the standard, what they call minimum transmission unit. So if
I don't think I'm quite on
it's a
networks
pretty
there.
interesting.
We didn't cover S-trace yet.
Read just means read that runs when you open it.
I remember path names.
Meaning that they start with a slash, and so what's referred to in Unix terminology and most other operating systems, what's known as a path name, is a way to navigate through this hierarchy of files and identify one particular one. And so that all comes to say that the low-level Unix operations that you use to implement this are to open a file, to read it and write it, and to close it. And those are the names of the functions. So the open function, then you give a path name. And remember, path names can be absolute, meaning that they start with a slash, and they go all the way down the hierarchy. They can be relative to a particular, whatever your current directory is, and they can also be relative to a user. If you use the tilde, slash, or tilde, then that's sort of a shortcut in this path name to get to particular users. So a path name can be any of those forms when you open it. It just has to be some way that, just like you specify in other places, that you tell where this particular file is you're trying to open. And so it's given a path name, and then it's given a integer that you want to do when you open this file. In what form do you want to open it? And that's specified by a series of constants that are already predefined when you include the proper files. And you can, and those actually get bitwise. Each of those is a 1-bit flag in some power of 2 position, or it's a position 1 bit in a field somewhere. And so you can logically OR those together if you want multiple combinations. So for example, I can say read only. I can say read and write. I can say append, meaning don't. If I'm opening it to write, don't start writing at the beginning. Start writing it wherever the end of the file is now. So all those can be done, and this is described in the book, by using the right set of names of constants and ORing them together. And that will return something that's called a file descriptor. And that's a very important idea that, and one of the reasons why we're talking about this today, this is going to be very important in your lab, is the notion of a file descriptor, which is just a small integer that lists which particular one of the open files that's being used by this particular program are you referring to. And so it's a small number because these are assigned sequentially when you begin your program and you run. And you're in fact limited on most machines to some bounded number of open files you're allowed to have at any time. In fact, if you go to, let's see, if you're on a machine and you type in limit, you'll see there that entry called descriptors. 1024, it says that you can't have more than 1,024 files open at any given time. And in fact, if you've got 1,024 files open, it's a chance you're doing something really seriously wrong, meaning that you haven't been closing the files you should be closing. And all the system calls, including these, always have a return code. And the return codes vary. Sometimes a negative number is an error. Sometimes a 0 is an error. They're all different and all confusing and all inscrutable. So you have to look at the documentation for every single one of those functions. And one of the rules we're going to hammer away at in this course is every time you make a system call, you should check the return code to see if there's an error and then do some appropriate way of handling that error. That's just a practice. It's a pain in the butt. It makes your code look like a rat's nest of conditionals. You really would rather not, because often there's an error, and deciding what you're going to do when there's an error is harder than just ignoring it altogether. And so there's a lot of code out there where people just cross their fingers and hope there's never errors in their system calls. But we're going to really push on you hard to say every time you make a system call, check the return code and do something if it's not right. And so the open will return a number. It's an int that it returns, but if it's a negative number, that means it couldn't open the file. For example, the file doesn't exist, or you're trying to open it in a mode that you're not authorized to open it in. There's three particular file descriptors associated with every single process that runs. One is standard input, the other is standard output, and the third is standard error. And they always have file descriptor numbers 0, 1, and 2. And so that you shouldn't really refer to them by their file descriptor numbers, even though you actually can reliably depend on those values. Similarly, if you want to close a file, so open, you see you give a path name and a one integer field that gives these flags that say something about the modes in which you want to open it. To close a file, you just say close, and you give the file descriptor number, not the name of the file. And it returns a return code too. So you might say, now why in the world could you ever get an error closing a file if it's open? And the answer is that actually can happen. In particular, we'll see when we have multi-threaded programs where it's possible to have essentially two programs running at the same time sharing their data structures and interacting with each other, sharing their memory. It's a very important kind of programming, and one that you can really make bad, horrible mistakes in. And one of the bad, horrible mistakes is if you try to close a file that's already been closed, it'll be an error. And that can happen if there's two different parts of your program running, and each of them tries to close the file. So in the book and in this code, you'll see we introduce some error handling routines, one of which is called p-error. And all it does is print some whatever message you want to print, and then it exits the program. Or no, I guess it doesn't. I'll mention it in a little while. It just prints an error message. But the point is, even something as mundane as closing a file, you should be checking the return code. OK, so this is the function that reads at this low level is called read. And it's given a file descriptor. You provided a pointer to a buffer that you've had to allocate either statically or via malloc. And you also specify how long that buffer is so that it can't overflow that buffer. And read just means read as many bytes as you feel like, but no more than the number I tell you to, which sounds like a weird statement. What do you mean what you feel like? Well, it has to read at least 1 byte. So if, for example, it's a standard input, it will hang there and wait until, actually with standard input, it will wait until you've typed in a string and hit the return. And it will then read at least some fraction of that into the program. If it's a network connection, again, the read will just wait. It will hang until something arrives on that particular network connection, and then read in some number of bytes that have been sent to it. And I'm being vague by saying some number, because the truth is there's no guarantee it will read any fixed number of bytes. It'll read at least 1, and it won't read any more than that buffer is. But the number between that might be variable. And so when it reads less than the maximum number of bytes you specify, that's called a short read. And that can and does happen, and you have to write your code expecting it. And we'll talk about that a little bit. And so again, read returns an assigned number, actually of data type s size t, like SSIZE_t, which is typically a long int, so a potentially negative number. And that number is, if it's 0, it means that it's detected an end of file, that you've run to the end of the stored file, that the network connection has been closed, or something has happened. If it's positive, then that's the number of bytes that were read, and if it's negative, it's an error code. So as I mentioned, if it reads fewer than the number of bytes you specify, that's referred to as a short count, and I'll talk about why that would occur. Writing is sort of the same idea, that you provide a file descriptor, you provide a buffer where the data that you want to write out is stored, and you give how many bytes long do you want your write to be. And it will write some number of bytes to the output, at least 1, and no more than n bytes, but it might not be all of them, which is kind of weird, because he said, I want to write this, I want to send it to a file, I want to send it over the internet, but it can potentially not send them all. And we'll talk about that a little bit. So again, that's called a short write. And similarly, it will return the number of bytes that were written, and so if it's less than 0, that's an error code. So just to give you a really simple example of this in action, this code does what you call echoing, meaning that you type in something and it will print it out. And it does it in the most mundane way possible by specifying a single byte reads and single byte writes. So you remember I told you read will read at least 1 byte, but no more than the number you've told it. So when you give it 1, it means it will read exactly 1 byte. And similarly with write, if you say write 1 byte, that's guaranteed to happen. And so this is really, really bad code, in the sense that call to read or to write the system level call is a relatively expensive call. It means kicking your whole operation up to the operating system, doing what's called a context switch, meaning it will go into the kernel of the system, invoke operating system functions, do whatever the read or write tells it to do, come back out, switch back to your job. And that will typically take maybe 20,000 to 40,000 clock cycles, which, a clock cycle nowadays is less than a nanosecond. So you say, yeah, you're talking maybe 10 microseconds. What's the big deal there? But that'll add up. If you start sending long files out over millions of bytes, if you start sending them 1 byte at a time, you'll spend most of that time sitting in the operating system going crazy. So this is not a good idea, but it does work, and that's actually an easy mistake you can make as a programmer is to use this low-level writing and reading, and the program will function fine. It's just it will be really, really slow. But just to give you a demo of this idea of calls to the operating system, there's a pretty cool. So this program, and this is on the web, linked off the web page, the code for this lecture. So this one called CP standard in, meaning copy standard input, is just the code I showed you. And so if you type something, it will just echo it back. So it's reading in. So it looks to you and to me like it's reading a line of text and then echoing it back. But what it's actually doing is, again, the interface to the terminal is one that it doesn't actually wake up this code until it gets a complete line. But it's actually just printing these characters back one character at a time. And I can demo that, but there's a pretty interesting facility called tracing, strace. And what strace will do, if you give it the name of a program, is it will detect every system call that you make, every basically call to the operating system functions that you make when you run a program. And it will generally spew out this huge amount of inscrutable stuff that you don't really want to see. I'll just show you this. It's telling you, logging every single call, and it's usually way too much stuff. So the more useful way to do this is to give it an argument that says, I only want to watch some limited class of functions when this is running. And so I just want our calls to the right, the low-level output right. And you'll see that what happens then is this string I typed in turned into a series of 1-byte writes calls to the low-level write function. So, and of course, some way I could show you the reads and writes. Let's try that. And it's all confused because I'm meshing. This comes out on standard error, but on the terminal it's sort of interleaving standard error and standard out, so it's kind of messy to look at. But again, you can see that it's taking my characters and it's reading one and writing one in this loop. So let's see, Control D to get out of it, back to the code. So what's this short count business? Why would that occur? Well, there's a couple ones. As I mentioned, if you counter an end of file, you're not going to read in however many bytes you're given for the buffer. If you were reading text lines from a terminal, the terminal handler will descend a line's worth at a time with the new line character terminating it. If you're reading or writing a network packet, the way network packets work is that, or messages, if you have a big long message, it's broken into smaller chunks, typically about 1,000 bytes or so. Question? If you try to read from an end of file, it will return 0. Is that a short count? It's a really short count, yes, but it's not a negative. Yes, so as it says here, if you encounter an end of file, it'll actually, there's two things actually, it's a really good question. If you're like near the end of a file, you have 100 bytes left, and you say read 200. Your first call to read will come back and get 100 characters, it would say 100, and it'll get that number. And then you call it again a second time, and it will return 0. And so that's how you actually detect the true end of file, as opposed to some other reason you might have gotten a short count, is if that you actually get a read of 0. The only case you'll get that for is an end of file. So that's a good question. Thanks. So again, if over the internet, typically packets are around 1,000 bytes. It actually depends on where it's gone through, what layers in the protocols it's gone through. But 1,500 bytes is actually the standard, what they call minimum transmission unit. So if you have a big long file, it'll come back in blocks like that. And if you're trying to read into a larger buffer, it will typically come back in chunks. Question? No, in other words, and again, if you're writing code, you shouldn't expect any number particularly. It will be dependent on the implementation. No, because I'm only reading or writing one character at a time, right? So I guess you're asking, what if I spent a week typing characters in a really long string and hit return? I don't know. If you try it, let me know the answer. But it won't cause an error. But that part, believe me, they've really gone through that code a lot of times and gotten rid of all those lurking buffer overflow vulnerabilities in the code. But we'll let you do it. I don't actually know. But you should write your code, again, expecting short counts as a possibility. And by the way, that's one of the headaches of using this low-level I/O is dealing with short counts. It's often sort of a nuisance at an application level. So you usually package this kind of low-level file I/O into other libraries that you're calling. We're only demonstrating this as the sort of lowest level in the stack. And writing also can give you a short count. For example, if you're sending packets over a network, it will only send as many as that packet can hold, and then return back to you. And you have to keep pumping them out to send the different packets. And so usually when you write code that uses this low-level I/O, you have to anticipate these short counts. So Professor O'Halloran wrote a package called Rio, and for now we'll just talk about what this package is. This is a package that you're really going to want to use for the final lab for the course. And so for right now, it's more of a high level. Here's an example of code that uses low-level I/O and packages up in a way that makes it a little bit more palatable. So Rio provides actually a number of different, two different levels of interface to the file, this file I/O. The lowest one is basically just a fairly small wrapper around the existing I/O, the reads and writes you saw, that will handle the short count issue. And so when you say with Rio, if you make a call to the read end function and you say some number of bytes, then that function will not return until it's read that number of bytes. So better be careful that many bytes are there if it's a network socket or a file, because it will flag an error message if it's, well, it will actually hang up if it's a network connection, waiting to read the bytes, or return an error if it hits an end of file when it's not expected. And similarly with write n, it's sort of a wrapper around the write function that will just loop until the short counts are taken care of. And then there's another class of I/O that's called buffered I/O. And this is what you really want to use in practice, and what you mostly use with the standard Unix I/O functions, is that you want to, within the user code, build up a little buffer of bytes that have either been read in but not yet consumed by the application program, or you accumulate some number of bytes in your program before it's actually shoved out into the file or out onto the network. There's two versions of that. One is a text-oriented, line-oriented I/O, and the other is just a byte-oriented I/O. So let's go through what these functions are and actually look at the code for them. So as I mentioned, the ones called readin and writein are just very thin. They have the same general semantics as the read and write, but they deal with the short count issue. So let's actually take a look at readin. So again, readin is given a file descriptor, a destination buffer, and a indication of how many characters, how many bytes it's supposed to read. And it's supposed to it's supposed to return, I guess it will return either a negative number if there's an error, 0 if it's at an end of file, or the number of bytes read. So I guess I was a little bit, I should have been more careful. If it hits an end file partway through, it will return a short count, but that's the only case. It won't return a short count if it could have read more bytes. So the main loop here you see is it keeps calling read over and over again until it's happy. One way it can be happy is if it's read as many bytes as it was supposed to read in the first place. The other is that if it hits an error code, and you'll notice that and that there's some subtlety of tracking which type of error that is, but in general, the common case is it will return the negative number indicating an error. If the number read is 0, then that indicated an end of file, and so what it will return is as many bytes as it's read, so it'll return the short count. And here it's just saying, okay, I've read this number of bytes, and increment and decrement the right value. So the point is it will keep looping, keep doing reads until it either gets the number of bytes it should, it hits an error, or it encounters an end of file. And you'll see it's checking for all these different error conditions for every call it makes. So this code, by the way, is sort of typical that it looks a little messy when you first look at it, but if you sort of study it, it all makes sense. So now let's talk about buffered I/O and what buffered I/O is. And this is a very important concept, so that's part of the reason we want to show you the code for it. So the idea of buffered I/O is that there's a buffer, meaning just an array of characters, array of bytes, that are allocated and associated with this particular file. And the program, if it's on a read, what it will do is it will fill up this buffer. It will give a read with a much larger number, with a large number, basically the size of the actual, how much memory you've allocated for this buffer. And the system will fill that up with up to that number of characters. And then when the user program wants to now look at this, get some bytes, it'll first check, do I already have some in the buffer that haven't been read yet? And if so, I'll just return those. And if not, then I'll refill the buffer. So the idea of it is, instead of every time going to the operating system and asking for one character or a small number of characters, the call to the operating system says, give me pretty much as many characters as you've got, up to some limit. And then I'll just go away and let the application program sort of pull these out a couple bytes at a time, but I won't bug the operating system to do it, I being the real function. And the way it does it is by just keeping a pointer that indicates what part of the bytes that I've already brought in from the operating system call, but haven't been supplied yet to the application program. And so in the sort of larger picture of things, if you imagine you're walking through a file, at any given point in time, this buffer will represent some range in that file, where the green is the stuff that's already been read by the application program. The pink is the stuff that's been read from the operating system out of the file, but not yet read by the application program. And the way this is implemented, once you think about it, it's not too hard to do, is that associated with every file connection then is a file descriptor, a count that tells you how many bytes there are that have not been read yet, a pointer to where this changeover is, and then the actual storage of the buffer itself, the characters allocated, the bytes allocated to the buffer itself. And so here's an example then of using Rio to do this echo, that you first read a line, and reading a line means it will look for and stop at a line feed character, and writing it back out. And again, if you do the demo of this code, it's a little, again, let me just trace writes because it's a little hard to see. The reads are hard to figure out with the. So you'll see that it's read the whole line, and now it's done at the operating system level. It's written just one chunk's worth, one call to the operating system's write function, instead of byte by byte. Okay, so again, I'm not going to go through all the code, but it's actually worth your while to do this. And by the way, I've actually done some applications where I took the Rio code. I wanted to add some features to it, but it's a very useful starting point to be able to build your own customized routines. Okay, so let's talk about some other parts of files. One is that associated with a file is what they call metadata. So the data are the actual contents of the file, the actual bytes inside of that file. But there's a whole bunch of other stuff that's associated with the file. Information about what type of file it is, what protection, read, write, execute protections it has, some information about the ownership of that file, what type it is, and also the times associated with it. When was it created? When was it last accessed? And when was it last modified? So that's known as metadata. And every file has that kind of information associated with it. And you can actually, and it's in a data structure called a stat. data structure. And you can, if you want to write code that then sort of probes the directory structure of a file system, you can make a call to the stat function, and it's given the path name of the file you want to stat, and then a pointer to one of these stat data structures, and then that data structure will get filled in by the information for this particular file. And then you can test various attributes about that file and see, basically get the information that's stored here. And there's all these nasty compile time constants that you use, or macros that you use to look at and examine these metadata. So here's an example. I won't do it, but it's a function called stat check. It's in the same directory. And so if you check some file, it will typically say, well, it's a regular file, and yes, you're allowed to read it. But now if I call chmod to set all the protections to 0, it'll say, no, you can't read it now. And so again, it's just making use of this data here. So now this is the part that gets a lot more tricky, is how are all this information about files actually represented by the programs? Question? Yes. Stat just I'll tell you one way you can find out what stat does. If you say man to stat, you'll get more than you want to know. So in general, if you say man stat, it'll give a Unix command that you can use to stat a file. So I can say stat dot, and it will print out some information about a file. In this case, my local directory. Let's see. I can stat any file here, and it will print out some cryptic information about it. But if you say man to stat, the Unix man pages are divided into different categories, and things that are system calls, Unix system library calls, are typically in section 2 of the man pages. And so that will return information about it. But the main point of it is stat is then a function that you call where you give it a path name and a pointer to a buffer that you want, and it will then fill in the contents of the buffer with the information about that particular file. And the form that it fills it in is one of these data structures called a struct stat. And that's pretty typical of a lot of these functions, is that they have some predefined struct. And if you want to get information, you allocate one of those structs, you pass a pointer to it, and then the library function will fill in the details. Does that make sense? Okay. Okay. So now let's look at some of the internal data structures that the operating system maintains regarding the files associated with the program. And this is a source of really nasty exam problems. I'll just warn you. So you're going to want to read this part of the book carefully, study the practice problems, look at the old exams, because I can guarantee you're going to get some of these on the final. That's a promise. And they can be infinitely obscure. So we can torture you with these. So the main point is that associated with any executing process, which you can think of a process as a running program, is a something called the descriptor table. And what that contains is, for every open file that you have, it has a pointer to a data structure called an entry in a table that's maintained by the operating system globally, which describes each of the open files. Actually, every time a file is opened, that allocates a record in this open file table. And so, as I mentioned, file descriptors 0, 1, and 2 have specific meanings, and the other files are other ones that you've opened during the course of your program execution and have not yet closed. So that's so each of these then is a reference to a particular open file, and it gives information about that file, and it also gives the position in the file that's currently, as I told you, every time you open a file, for a regular file at least, there's an associated position of where in the file was your last read or write, or where would you be your next read or write. And so that's the file pos. And there's also a reference count, which is used by the operating system to keep track of, because we'll see it's possible to have multiple processes sharing an entry in this open file table. And it uses this reference count, which is a standard way of keeping track of memory allocation, to know when it no longer needs that entry, when there's been enough, when the file is no longer accessible, and therefore this entry is not needed. So for every one of your open files, it will have an entry in this table. And this table, as I said, is shared across the whole operating system. And then associated with every file is called a vnode, which stands for virtual node. And this is where that contains the sort of information about this file, in particular, where is it stored, this information that you can get from stat and things like that, how big it is, and things like that. So that's for every file in the system actually has a vnode entry, whether it's open or closed. Now this can get complicated. So for example, if within a single program you call open twice on the same function, you'll actually get 2 different file descriptors. And you'll be able to access that same file and have 2 different positions in it. And it makes sense if you imagine you're reading from a file, and you might want to read from 2 different positions in that file within the same program, and you can do that. That's perfectly legal. You just call open twice, and that will keep track of 2 different positions. So the point is these file descriptors might be referring to the same file, but they're actually at different positions within the file. And that can happen also if you've opened a file for both reading and for writing, and you're writing ahead and then reading bytes that have already been written. That makes sense. It's not such a good idea to have 2 different file opens that are writing simultaneously. You can mess up the file pretty badly that way. But there's nothing in the operating system that prevents you from doing that. So it's not a good idea, but it's a legal operation. So that's the point, is you have to distinguish at what level is sharing taking place. And you see that if you have 2 different table entries sharing one file, then what's different there is that you can be working at different file positions. Similarly, of course, the more common thing is you have two different open files, and they're referred to different files. But now, and this is where life gets exciting, if you call fork, you remember about fork that it spawns a child, but the child inherits a lot of information from its parent. And one of the things it inherits is its descriptor table. It gets a replica of that descriptor table. And so now both the parent and the child have identical entries in their descriptor table. And so they're sharing files, but not at the file level, but at the open file table. And what that means is if the parent does a read, it'll bump along the file position. And if the child now does a read, it will see this from this new position. So you can see why the exam problems get really interesting. That we'll keep track of all these different possibilities, and they'll do different things. And then, of course, the parent or the child can start opening and closing their own files as well, and that will get very messy. And here's what you see the reason for having reference counts here, that if you have a lot of forking going on, then you can create multiple pointers to this table entry. And in order to really, really close the file, each of these has to call close before the file is truly, truly closed from an operating system perspective. So there's other fun things that make life interesting, too, and contribute to the exam problem possibilities. One is a call called dupe2. And the purpose of dupe2 is to excuse me, duplicate a entry in the descriptor table. And the most common use of that is IO redirection, the either greater or less than sign to either read the instead of from standard input from a file, or instead of writing to standard output to write to a file. And the way the operating system actually implements that is shortly after starting the program, it will call dupe2 to make it so that the file descriptor 1 is not the standard output of the for this process, but it's actually the original standard output, but it's actually a descriptor for the file that it's supposed to write to. And same with if it's doing input redirection. And, but you can call dupe2 yourself and do these kind of things, and there's actually good reasons for doing so. So in particular, imagine I open a file, and standard output points to the sort of normal thing. And I open a new file, I call it B, and then I call dupe2, excuse me. And now what both file descriptor 1 and file descriptor 4 are sharing this entry in the file table, and you see the reference count of 2. And so in order to really close it then, what would typically happen at this point is this happens before it starts your program. You'd want to close file descriptor 4. And in fact, there's a lot of bugs you can make by not closing files. And it's easy to make mistakes when you have multiple entries in these tables. Yes?
So by doing that on the previous slide, don't you lose the reference to standard out?
No. See, if I close this one, it just decrements this reference count. But this remains a valid entry here.
Right, but wasn't standard out originally pointing to a file A?
Yes.
So
But dupe2 will decrement the reference count of the original. So dupe2 goes backwards from where you think it should. So dupe2 is the, I want what I referred to, for example, file descriptor, I want file descriptor 4 to become what I can use to and refer to with file descriptor 1 here. It will actually decrement the reference count of this before it then does the copy. Otherwise, it would create like an orphan in this table, right? So anyways, dupe2 also is a powerful but dangerous mechanism. So now, finally, let's just mention the much more common I/O that application programs use is what's known as the standard I/O, and that's what's documented in KNR, and it's actually part of the C standard, all these different functions. And so the main feature it adds is sort of like what you saw with the Rio package. It adds buffering, so it doesn't have to do this low-level stuff, and it avoids some of the nastiness. The way it works is what we've already seen. It uses buffering to do the I/O. And so it doesn't have to do this low-level stuff, and it avoids some of the nastiness. The way it works is what we've already seen. It uses buffering to do the I/O. So just as an example, here's some code that calls printf one character at a time to print the word hello. But if I run that and I strace it, you'll see that there's only one system call to write. And it works the same way you saw with the real code. It builds up a buffer, and it's not until this call to flush that forces the output to actually be a printed output. Usually that happens automatically, actually. If you print a line feed, it will flush it. So I think that call to flush is probably redundant here. So, and so that's the benefit. So buffered I/O is much more efficient because because of the buffering. as a result, we've now seen three different types of I/O. There's the low-level I/O referred to as Unix I/O. You saw this package that was written specifically for the book and for the course called Rio. And then there's a much larger and, in fact, richer set of I/O functions provided by the Unix standard library. So you might ask a couple questions. One is, well, why the heck did you write this when you've already got that? If Unix provides buffered I/O, why did you do it yourself? And the reason is this stuff it works really well for the I/O you do to a terminal or to files, but it doesn't do very well with network connections. It wasn't really designed for that, and so it gets really messed up. And so the main reason you're going to find yourself using this is when you're starting to use network connections. The other thing is these do not coexist very well, buffered I/O with Rio I/O, because they each maintain their own buffers, and they don't know about each other, and they get terribly confused. So you kind of have to pick one or the other with respect to any particular I/O connection, and don't try to mix and match them. So like I said, Unix I/O, then the low-level stuff, from an application perspective, it's like really painful to use, especially with short counts and error codes and all that stuff. And so in general, you want to either write your own package or use some other package around it. And so as I said, standard I/O gives you printf and scanf and all these nice features. It's uniform. It exists on all systems. It's reasonably standardized. So in general, then, use the standard I/O for most of your day-to-day uses of files. Use raw I/O for low-level stuff, like when you have to. And partly, it turns out signals are not you shouldn't use standard I/O when you're writing signal handlers. And then the Rio you're going to find useful in particular for doing networking. One other thing that you should, one bug that students do over and over again in this course is they try to do line-oriented I/O on things that aren't lines. So like a JPEG image or something like that. And the reason that's important is that these functions treat the end-of-line character, 0A, as a very special character. They'll stop reading or something like that. Or if it's going between Windows and Unix, it will actually change one from carriage return or from line feed to carriage return line feed. Similarly, functions like strlen and strcpy will stop when they hit a null byte. And that's not what you want to do when these are network packets you're trying to send out. So be careful. Some of the functions you've used a lot and you're very familiar with may be completely inappropriate for things where you're doing binary data or you're communicating over networks and things like that. So be sure you understand what you're doing when you start to use these kind of functions. So those of you who really want to know this stuff, there's a fellow named Richard Stevens who unfortunately died quite a while ago. But his books live on, and there's various people who have signed up to become co-authors with him in his absence, and creating new editions of these books that used to date back way far. So, and if you really want to know how this stuff works, you want to be the ace programmer, these books are the best you can get. But I'll also warn you, your bookshelf will become very heavy laden because there's the volumes 1, 2, and 3, and then there's networking books, and Stevens is like an encyclopedic reference, but they're excellent books. If you really want to understand something, read Stevens. And there's another book that is just specific to Linux that's fairly nice and somewhat, it's very detailed, but since it's only trying to deal with Linux, it's a little bit less weird than trying to read Stevens, because Stevens will say, in this version of Unix it works this way, in this version it works that way, and blah, 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 and it's all different, and it will drive you crazy. But Stevens is still an outstanding set of books. OK, so this is an example, and I'm not going to go through it, but these are the kind of things that we use to torture students, that you open some file descriptors, and you do some dupes, and you do some forks, and so you end up with a real spaghetti for all the pointers and what's shared and what's not shared, and then you ask, what will this print? And of course, you have to trace through in great detail what's really going on. So those are in the book, and I recommend you work on some of those. OK, that'll do us for today, then.
Okay, again, I read all of Karisk's book, and nothing really stands out in this lecture that is new material for me, other than the RIO package, which is a creation of one of the instructors. One thought occurred to me is the difference between line buffering and libc buffered I/O and line buffering inside the kernel, because I think maybe this is in TTYs, not in the kernel itself, but I think TTYs are technically implemented as part of the kernel. They just don't run in kernel space, if I'm correct. I don't know. No, I think that they have to run in kernel space. Anyways, yeah, because the kernel will get like the interrupt from the keyboard and it'll write into the TTY. And then the TTY has to, like, if you're reading off the TTY, it has to do its own kind of like buffering, line buffering, so that you don't get reads that are partial, I guess. I think there might be some buffering going on in the kernel with TTYs. And if I recall correctly, when I read Karisk, we read into that. But I guess that's it. It just occurred to me watching this lecture that is an area that I don't necessarily have complete full understanding of. But I do understand that there is line buffering in libc. So when you're writing to libc with using buffered I/O, like you're writing to a buffer, and then that buffer gets periodically flushed. If you write like a new line character, it'll flush it, or if you can call fflush. But yeah, there wasn't really anything in this lecture that was like new to me. or provided any details. So really, this is just kind of like I watched it just to watch it. But let's move on to virtual memory. This is where I actually think I'll get some value, and virtual memory is something that I will be reading in the book. It'll be the last chapter I read in the book. So let's start on the virtual memory. We want to start on the virtual memory, or we want to do recitation 9? Let's do recitation 9 because it involves I/O before we move on from all the I/O stuff. I doubt we'll get anything out of this either, but we'll see.
So today's recitation is on exceptional control flow. So you just had your midterms last week, and now the next lab is out, Shell Lab. And Shell Lab will require you to understand things about exceptions, exception handling, exceptional control flow, and also stuff about I/O redirection. You'll be writing your own little shell. So there's a lot of slides in this. I'm going to go through them kind of fast so that we have time to talk about Shell Lab at the end. But if we get to a slide and it's something that you don't understand, or you want me to slow down and re-explain a bit, just let me know and I will go over it in more detail. But you should have seen most of this in lecture already. So, okay, yeah, so midterms scores are on Autolab now. There was a period of time where we had released them but not released them, so everyone had zeros. So you can check again, your actual score should be up now. You can view your exam if you want to review how you did in office hours, just in Mean 5207 or normal office hours room. We'll be able to let you look over the results again and what the correct answers were if you missed anything. And if you want to make a regrade request, if you feel that you should have gotten credit for an answer and it didn't give you credit for it, or that the credit it gave you was wrong in some way, then you can submit a hard copy written request to Professor O'Halloran. You should do that this week. You should, if you go to his office and he's not there, you can slip it under his door. The process for that is outlined in the course syllabus, too, if you want to read it there. But it needs to be hard copy written request, and that is even if you've already emailed the staff list, or if you talk to a TA after your exam, you should still make sure you do that so that we are able to process your request. Okay. So up until now, we've had 2 mechanisms for changing control flow in a program. You've seen this in your bomb lab and your tech lab. You can do jumps to jump to a different part of the test. For loops, while loops ended up turning into jumps with conditions. And then you also had function calls and returns from functions, which are another mechanism of control flow. And those react to changes in your program's state. So the jumps are either an unconditional jump, or it's a jump based on some condition of the program state. And the call and return, in the same way, they are controlled by as the program executes. And state changes, it will go into a branch that has a call or a return and do that. But we want to be able to do more than that. In order to have a complete system, we need to be able to react to changes in system state. So the system a computer system has more than just programs in it. It also has hardware devices that might have changes. You might be reading or writing to a disk. You might be getting information from a network adapter, and you need to be able to react to those changes because those are external to your program. You might have an instruction that when it executes, it causes something bad to happen, like you divide by 0, or you try to access a piece of memory that's not valid for being accessed. That's something that you need to be able to react to. The user might send signals by keyboard commands, so they might hit Control-C or Control-Z, which send different signals. You might have system timers, and so you need to be able to have mechanisms for handling these exceptional cases, these exceptions in control flow. So there's a couple different classes of these. So there's asynchronous exceptions, which are called interrupts, and these are caused by events that are external to the processor. So this is stuff like I/O. If you're reading or writing to a disk, it can send you asynchronous exceptions. If someone hits the reset button on the computer or Control-Alt-Delete on like a Windows PC, that sends an asynchronous exception that needs to be handled. There's the synchronous exceptions. So the synchronous exceptions happen as a result of executing a particular instruction. The asynchronous exceptions, they happen whenever. You can't look at the assembly code and say there might be an asynchronous exception here because they just happen wherever the hardware device happens to send it in. The synchronous exceptions happen because of a particular instruction being executed, which has a certain result. So there's a couple different kinds of these. There's traps. So a trap is an intentional exception that we cause to happen. So for example, system calls. We want to be able to make calls to certain system functions that allow the kernel to do different management of the system that's more than just what a program does. So this is stuff you should have seen in class, like when we do a fork or an exec. The kernel needs to be able to set some stuff up. And so we make a system call to those functions, and that actually takes control out of our program for a bit, lets the kernel do its thing, and then we return to exactly where we were before. We also can handle breakpoints this way. So the way GDB is able to set breakpoints is it makes it so that every function call ends up being a trap, and then it handles that trap by pausing execution of the program, letting you do what you want in GDB, and then it will continue it when you choose to continue. Then there's some special instructions that can cause it, but then in the end, after the trap, we just return straight to the next instruction and continue executing like we were before, which is, this is the idea of it being synchronous. And then there's also faults. So faults are things that we didn't intend to happen. We weren't necessarily expecting it to happen, but we might be able to recover from it. Anyway, we might be able to keep going. And so some examples of this are page faults. So you'll learn more about the virtual memory system later. But what has to happen when we access a memory is it needs to be loaded up by the virtual memory system as something that we can access. And the first time we access some particular memory, the virtual memory system doesn't have it ready yet. And so there will be something called a page fault, and the system will go ahead and make sure that that memory can be used. And then we continue on executing, and everything's OK. And you'll learn more about the details of that later. But that's something that needs to happen. It's sort of like the same mechanism as a cache miss. It's not in there. You have to load it up, and then you keep going. But then we have other things like protection faults. So you could see this in the form of a seg fault if you try dereferencing null. Null is a address that you're not allowed to write to. And so what will happen is you'll get a fault, and you can't recover from that. Your program is going to have to stop because there's nothing you can do. You might also see this in a floating point exception. So if you divide by 0, that causes a floating point exception. Or if you mod by 0, that causes a floating point exception. And so then you can't really recover from that. You'll get a fault. And then what you can do, so what happens is if the fault was recoverable, so in the case of a page fault, it re-executes that same instruction. So if you tried to load a memory address and there was a page fault, then of course, once you've got that page loaded up as it's supposed to be, you want to re-execute the same instruction so that that thing actually happened, because the first time it wasn't able to do it. Otherwise, if you're not able to recover from it, your program will just abort. So a seg fault or a floating point exception will typically, you'll just see your program stop running. And then there's the unintentional, unrecoverable errors that are aborts. This is stuff like if your RAM gets corrupted, there might be a parity error. So the RAM is sort of keeping track of some information to make sure that it's staying in a correct state. And if it notices that something got corrupted, well, there's nothing you can do about that. You can't really get it back, so it'll just abort. You don't see these too often. I guess you could maybe make them happen if you're like physically messing with your computer and like taking the RAM out while it's running or something. I don't know. These aren't things that you cause by bad programming. They're sort of things that happen when the hardware goes wrong. So you don't see them much because usually hardware is pretty good, but if you have bad hardware, you won't see these. So okay, so what's a program? So we have, in our system we have programs. So the program is, the executable binary file that we've compiled, and it's written according to a specific specification. So in the case of Linux executables, it's a format called ELF. So we've got the specification. It tells us, has the instructions in it. It tells us what the program is supposed to do. The machine can read it, and it's just this static binary file. The program itself is just this static sequence of bytes. But then we actually, need to execute it. So then we have a process, which is an instance of a running program, and then the process, in addition to, having that static program associated with it, needs to have a sense of its control flow, where it is in the execution of this program. It needs to have its own address space, the memory locations that it can access, and what's in them. Now there's an abstraction of virtual address spaces. So this is something we'll talk about later. You don't need to know the details about it now. But essentially the computer makes it so that every program can pretend it has access to all of memory and nothing else is using it. So when you have these addresses, if you're running two programs at the same time, you might see something like they're both accessing the same address and reading to and writing from it, or reading from and writing to it. But it's not actually the same address. Underneath, the machine is actually mapping these to real physical addresses so that everyone has their own unique space. But everyone can pretend that they have everything. Yeah, and then you can have multiple processes running at the same time through concurrency. Okay, so let's see. So 4 basic states of processes. So processes can be running. So it's the one that's actually executing instructions on the CPU right now. The number of processes you can have running at once is bounded by the number of CPU cores you have. So now that we have multi-core computers, we can actually have 4 processes if you have a quad-core computer running literally at the same time. But then if we, if we have 8 programs open, only 4 will be running at any given time at most, and then the rest might be, runnable. They're waiting to be running, and they're just going to switch between them. They might be blocked, waiting for input or some event to happen, and then so they're not runnable when they're in the blocked state. And then there's also the state of zombies. So I think did you talk about zombies in class? Yes. Yes. Okay. Yeah. So then there's the zombie state. So when a process terminates, it becomes a zombie until it gets reaped. And so the process sort of stays around so that the process that called it, its parent, can take a peek at why it exited if it cares, and then it should get reaped, and it'll cease to exist as a process. So okay. So there's some basic control functions that we have, and these are things that you'll be using during shell lab. So we've got forking, execing, exiting, and waiting. We have these are standard Unix processes. We have some version of these on anything that's Unix or Unix-like. And then we also have wrappers for these, error handling wrappers for these that are the same name except with a capital letter provided by the csapp.h file, which is on the website. So what do these do? So we have fork. Fork takes no arguments. It returns an int, except it's interesting because it actually returns twice when you call it once. Because what it does is it creates a new child process that's identical to the process that called it. So essentially it takes the process that you currently have and it clones it, and then it lets both of them run at the same time. So the entire state is duplicated. All of the memory becomes unique. So now, if we change a pointer in the parent, that change is not reflected in the child. They have unique memory, unique address spaces. The registers at their current in their current state are duplicated, except for the return value is going to be different based on whether it's the parent returning or the child returning. That's how you can tell the difference between the two, is the return value. And then file descriptors. So have you talked about file descriptors yet in class? Yes? No? Yes? Okay. So the file descriptors are unique. So if you change those around, that's not reflected in both. But the actual files that they're pointing to are shared, of course. So it's not making a copy of the files on disk. If you're modifying the same file from both the parent and the child, it is still one file on disk. And so you get equal but 2 distinct states. And then, of course, it returns twice because the parent returns and the child returns from this fork because they're both able to go off and do their thing. And then you can use the return value to do the control flow of making the child do one thing and the parent do something else. So here's an example of fork. So it returns 0 to the child process, and it returns the child's process ID to the parent process. So if the parent wants to keep track of what happened to the child, it now has an ID to keep track of it. So we have something here. We do a fork, and then we're doing a conditional based on the return value of the fork. So if it's 0, then we know it's the child. So then the child would print hello from child. And if it's anything else, then it's the parent. And so we print hello from parent. And so this way, both will print based on which one they are.
A thought just occurred to me. I've used the Puma web server, and they had options for running both threads and processes. Why would you want to mix the two? I guess the crashing is a good reason. If the Ruby interpreter crashes for whatever reason, you'd only take down that process and it would get restarted versus taking down the entire server. Concurrent computation is limited, in threads in MRI because of the GIL. Yeah, from my perspective, like, I look at the two models, full processes and threads. They're very similar. Um, if you're cloning for a thread or cloning for a process, I mean, they obviously have very clear, distinct differences. But I would think the benefits would be to use threads. If you're using a threaded model, if your code is thread safe, then why not just use threads? Because they're lighter weight than full operating system processes. But there's a problem in blast radius of crashes and something that I didn't immediately think of, which is the GIL that's in Ruby, which limits concurrent computation, or we should say it significantly limits parallel computation, because you can't be running more than one bit of Ruby code at any given time. So effectively in the Ruby code, you don't have any parallelism, but you can be running C code that also uses P threads that does stuff in parallel. So I think the blast radius and the GIL are the two reasons why you mix the two. But in a language where you don't have like a global interpreter lock, the parallelism argument, parallel computation argument goes out the window. Also, most of these Ruby apps are very I/O bound, so it's not going to be a huge benefit to have those processes. But the blast radius thing, I think, is a really good reason to have separate processes. But again, in a world where we have these massively scaled applications where you have thousands of nodes, one node's entire server going down is not going to hugely affect the overall performance of the system. At least it shouldn't. And even if you can reduce that, it's just a small constant factor, like a 1/4, or it's a constant factor that you improve it. So I guess, there are reasons to mix the two, but having a pure threaded model, I think, is what I would default to. Because your workloads are mostly I/O, and you have a distributed system where taking down an entire server is not the end of the world, or at least shouldn't be. But if you can do it for free, why not, I guess? And in much smaller scaled systems, like if you have a single server, then yeah, you don't want to take down the entire server if a process crashes.
actually this can happen in either order. The order that they return in child or parent is whatever whatever happens. The system gets to decide that arbitrarily, and so we could see these two print out in either order. And that's something you're going to have to think about while you do your shell lab, is making sure that things are not happening out of order in a way that will mess up your program. So then another thing we have is exec. This is the second class of system call. So exec replaces the current process's state and context with a different one. So essentially, it turns one program into another. If that one program, if we're running a program and we want to just say load up another and now start running this thing instead, that's what exec does. And so we never return if it executes successfully. So we call it once. Fork, we called it once and it returned twice. Exec, as long as it works, we call once and return 0 times. If it fails, we'll get an error code, so we will get a return. But otherwise, we never return from the exec because now we're running a different process. Essentially, well, we're running a different program. It's in the same process, but we're running a different program, and that's the program that's going to execute. So yeah, so exec VE is going to be the one that will be useful to you for shell lab. And this is sort of how you're writing a shell. The shell takes in a program on the command line and then it has to run it. So sort of the idea is that you can fork off a child, and then the child can exec this program, and that's how you get the program to run. And then the parent remains as a shell. And so this way you can, every time you run a program, you get a new process that then turns into what that program is to make it run. This is sort of what you'll be doing. And there's another one, exit. Exit is pretty easy. You give it a status, which sort of can be used to indicate what sort of error it was. 0 is typically uses the error code for there wasn't an error, everything was okay. And when you exit, what it does is it causes the program to terminate and reduces the process into a zombie state. And then it frees all the resources, it frees whatever memory, whatever file descriptors, becomes a zombie, and then it'll just sit around until it gets reaped. So the parent process can check what that exit code was, if it wants to do something based on it, and then reap it. Or if the parent has already died before the child, there's the program that's sort of the base program that everything is a descendant of, which is called init, will handle reaping it, so that it doesn't just sit around forever. And when this happens, a signal is sent to the parent, so that the parent can use that signal to know that it has something to check. And then the last one is wait. So wait suspends a process until one of its children terminates. So exit sends the signal to the parent when the child terminates. Wait is how the parent can sit around and wait for that signal to happen and then do something based on it. So wait will return a process ID based on the process that got terminated. And then you can do something with it. So there's different variants of this, and you can check the man page. The one that will be useful to you for shell lab is wait the ID. Yes? So what's the point about your is it beneficial? So why can't you just why can't you just when it dies it's dead and you don't have to do anything more? So it's the parent might want to be able to check what this exit status was. So say you have a parent that's working off children, it might want to be able to do some error handling if one of them exited in a particular way, or modify its state to know that hey, a child exited. I now know that I don't have this child around anymore. And so we just keep the zombie around when the process is closed. Even before it's reaped, it already frees the memory and everything associated with it. But it just sticks around because it needs something to have that exit status sitting there until it gets that gets handled and we know we don't need that anymore. Why do we need to read it? So and it will take care of it if the parent is already dead. But if the parent is still alive, then the parent might want to do something with it. So the parent gets its chance to do something, and then it'll die. So yeah, so here's this example. Yeah, we saw this before. This is a variant of the example that we saw with fork. So sort of, this is an important thing. Fork will give you the child and the parent in either order. You're not guaranteed that you're going to get the one order or the other. So when we execute this code, we can see that it might print child first and then parent. If the child was the first one to return, it might print parent and then child. So a question for you to think about is how do we get the child to always print first? Yeah, we can use our other system calls like wait in order to make it so that the parent won't print out until it's received the information that the child has terminated. So then the child has already printed, and then the parent can go ahead and print. So that's the sort of stuff you'll need to be doing in shell lab, is just making sure, yep, here it is. We just wait till the child terminates, and then the parent can inspect the exit status if it wants, and then it can print out parent. So now we'll always get child parent. Okay, let's see. So here's an example of using exec VE. So we use exec VE. What we're doing is we're running ls. So ls being the great Unix program that lists the files in your current directory. So we give in, this is the path to ls, this is where else is stored, and we're putting in the -l flag as a command line argument to it. Okay, and so then the question is, when we do exec VE, will the child ever reach this below the exec VE? Will that ever happen? Any ideas? Yeah? No. Okay. So yeah, that would be
possibly
the normal case. What if exec
VE
VE fails?
doesn't fail.
Then yes, yeah. So as long as everything goes great with exec VE, it'll never reach there. The only case that exec VE returns is when there's an issue. So we can sort of, we can find that by, I think it's man 2. We can see that by looking at the man page for exec VE. It tells us what it does. So it'll tell us what happens if it fails. But in the normal case, yeah, we never go below that. If we had code down there, it wouldn't ever get executed. So this is a way to make ls happen, and then the parent continues on doing whatever it was doing. Okay, so this is sort of a depiction of the hierarchy of the processes. So the process that's sort of the parent of all of the other interesting stuff is init, which has process ID 1. So that's why init is responsible for reaping anyone whose parent is already dead, is because init is an ancestor of everyone that's running. And then init also, so init gets stuff that's running in the background, sort of your system stuff that make the computer work. And then it's also running the shell, and then your shell has all the stuff you're running and anything that those things are running. This is sort of a simplified picture, assuming you're just doing a command line computer. This doesn't include what would happen if you have like a display manager and all sorts of stuff. But this is all you need to be able to. This is sort of the part you'll be working with for shell lab, is the shell, and then children and potentially grandchildren and such. So okay, so signals. So we need some mechanism for passing around this information from to the processes that these things happen for this exceptional control flow. So the things that we have are signals, and they're really just numbers, but they're numbers that each one is assigned to a particular meaning of this is what happened. So yeah, so we can send these signals as from processes to other processes, and the kernel will do that, and then we can handle them. So some ones that you might have seen before, there's a sig interrupt. That's what you get when you do Control C, which the default action is just terminate the program. You've got sig_kill, which is a stronger version, which says terminate the program, and you can't do anything to override or ignore this one. So sigint, you can write a handler that says do something else with it. Sig_kill, you can't do anything about it. When you get that, it's going to kill it. You've got the sig_fault, so you've seen that one. Sig_alarm is when a timer signal happens, or sig_child. So sig_child will be sent as the signal to a parent when its child is stopped or terminated. And the default action is actually just do nothing with that one. But you can write a handler for it so that you can actually then do something when child changes state.
What is it for being exception when signal?
So, okay, so let's see. So signal, so the exceptions, let's go all the way back. So we had these exceptions which were sort of called, these exceptions were caused by like hardware in the asynchronous case, or as the result of executing a particular instruction in the synchronous cases. In a signal, it's something that's actually not coming from the process executing instruction, but it was sent to it by something else. So by another process, for instance. So like an asynchronous hardware exception would be like when a read or write event happens to a disk, whereas a signal would be one process is sending a signal to another.
But the second violation, the 6
Mhm.
wouldn't that be the same thing as the fault, the unprotected,
The protection fault?
Yeah.
Yeah. So let's see. So protection fault. Yeah, I'm actually not sure of the exact relationship between them, but it might be that the protection fault generates a 6 or something. Yeah, I'd have to check, but they're similar. I'm not sure of the exact relationship. Okay, yeah. So the kernel is what's in charge of sending these. So the kernel, of course, is the sort of the control unit of the operating system that manages all of these processes, and it's able to send a signal to a process just by updating some state that it's keeping track of for that process, and it can happen for whatever reason. And so then a process can receive a signal. So one important thing about signals is that signals don't keep account of how many of that signal have been received. It's not like you have a list of I've received 5 sig_kills. What you get is the signal has been received and we haven't done anything with it, or there is no signal. And so it's just it's a true or false for every signal. If we send it multiple times before anything is done with it, the fact that we sent it multiple times is thrown away. We only know that it has been sent at least once. So signals are received at a context switch. The time that signals are actually dealt with is when the process is changing context from one to another. They don't get dealt with immediately when they're sent. So it's sort of just every time we switch a context, we check and say, hey, are there signals to deal with right now? And there's 3 things we can do with it. We can ignore it. It's easy enough. We can just kill the process, or we can have our own handlers that we write and catch the signal and do something with it. So this is sort of the software version of handling hardware exception, asynchronous interrupts. Let's see. Yeah, so we can block signals. So there's a function called sig_procmask that allows us to just ignore signals and say we don't care about them. If we want to run some code that shouldn't ever be interrupted, we can wait until we get a particular signal with sig_suspend. So when we call sig_suspend, what it'll do is it just won't continue executing that process until that signal is received. The kernel will start it up again once it gets that signal. And this is good because this allows us, it would be a bad idea to wait for a signal by doing something like having a loop that just continually checks if that signal has been received or something weird. Because that'd be really expensive. It'd also be a bad idea to just like tell the program to sleep for a couple seconds and then check if it's been received and sleep for another couple seconds. Because then then you're sort of not necessarily handling it when it happens, and you end up with race conditions, and it's slow, and that's really bad too. So you shouldn't do either of those for your shell lab. If you think of those things, don't do them. sig_suspend is the way you should be handling it. If you want your process to just not do anything until it gets a specific signal, you get to a point where you're just like, now I want to wait for sig_child. Then you should use sig_suspend and wait for sig_child with that, and then you'll start up once you get that. And you can't modify the behavior of sig_kill and sig_stop. So those are particular signals, and you can't write a handler for them that does something else. sig_kill and sig_stop will do their, they'll kill your program, and you can't do anything about it. Which is good, because otherwise you could write a program that like just ignores all signals and never dies, and that would be unfortunate if there was no way to kill the program, because then like what do? You have to reboot the whole computer to get it to stop. So okay, so signal handlers, you can write your own handler for a particular signal. It's separate of the flow of control in the same process. So sort of when a signal handler happens, you go and you execute it, and then you continue back where you were, executing the process before the signal handler happened. And you sort of jump out, do this thing, and then jump back to where you were before. And it can be called anytime when the signal is fired. Okay. So here's what I said. Don't use sig_suspend when that's what you want to use. Don't do something else. So you can't use wait twice in order to wait for a signal. Sig_suspend is what you want there. Let's see. So so you can read the details of this in the man page. I want to get to the shell lab stuff still. And every process, so we've got process groups. So every process belongs to a process group, and when we fork, we stay in the same group as the parent. So and then you can change the group, but by default we just stay in the same group as the parent, and that will be something you'll do in shell lab. Let's see. So what do we have here? We had a job. Move a job. Okay. So here we have some code. We fork. The parent adds a job to a list of jobs that this child exists, and then when the child exits, it's supposed to remove itself from the job list. That's what this is doing over here. So when it exits, it'll remove itself. The parent is supposed to add it. But what's the potential problem with this, based on what we know about fork? Yeah. Right. Yeah. Depending on the order these happen in, we might actually have the child removing itself before it gets added. So it removes itself, and maybe that causes bad things to happen because it's not actually in there. Or maybe it succeeds and then we add it, and then it will never get removed because it's never going to return again because it's already done. So we want to sort of block signals in this code to guarantee that we won't be adding it at the wrong time. So we can block sig_child, unblock it, and unblock it after the add job. So of course, since we're forking, depending on which one we go into, we'll want to be able to unblock them both. But the idea is that we make sure that we have sig_child blocked before the add job, and we don't unblock it until after. So that way, if the sig_child actually happens, we'll make sure that we have added the job before we removed it. Okay. So now let's talk about shell lab for a bit. So shell lab is out. It's due Tuesday, November 3rd. So that's a week from tomorrow, right? And we've given you quite a bit of code already. more code than we've ever given you before, and it implements a lot of the boring stuff that will be helpful to you. So there's a lot of stuff in terms of like just managing the list of jobs. What you're writing is a shell. You're writing a shell, you'll, just like a normal Linux shell, and you'll be able to put commands on it, and it'll run the program. And you'll be able to run arbitrarily many programs in the background at once, and up to one program in the foreground at once, sort of like just like a normal shell works. And you'll have a list of jobs of all the things that are currently running, and we've given you a lot of the stuff that handles that list of jobs and all that, because that's boring. But don't be afraid to write your own helper functions. In fact, you probably should be writing your own helper functions. In addition to the stuff we gave you, don't try to just shove the rest of it in main. It'll end up being longer than Cache Lab for sure. So you want to make sure that you factor it well. Reading man pages and reading in your textbook about these different system functions. A lot of this lab is just understanding how these system functions work and where you're supposed, what they do, and how to, picking the right one based on what you want to happen at different points in your program. So these are all ones that will be useful to you, listed here. So you should make sure you've read the man pages, read the appropriate part of the book that deals with all of these, and that you know how they work, so that you can, use them properly. Don't use sleep to solve synchronization issues. So sleep is a function that just we can look it up. Sleep, what's something we want? Yeah. So sleep just makes your process stop running for some number of seconds, and it starts running again. One of the things that can happen in this lab is you have issues where, maybe you've removed the child before you've added it. The proper way to fix that is not to make the parent just sleep for 10 seconds before it, or make the child sleep for 10 seconds before it runs, and then hope that in those 10 seconds it gets added. Because, first of all, that's going to make your program really slow, because now it's going to have to wait that amount of time to do anything, even if it's like something that's really fast. And also that's actually like not correct in terms of fixing the issue, because if something still takes longer than that, then it still is a problem. Like you haven't fixed it, you've only you've said hopefully it'll happen faster than this, but it might not. And so that's, it's incorrect, and it's slow, and there is a way to do it. And so you should think about how to, use signal masks and sig suspend or whatever is appropriate in the case to actually make things happen at the right time. And our grading code also forces things to happen in different orders so that we can test to make sure that you will do it right in the different orders. So some hazards is these race conditions. So race conditions, that's the name for these issues where things can happen in multiple orders, and the order happens in actually makes a difference in terms of the correctness of the code, the final result of the code. So you should, you want to write code so that there are no race conditions. You should write it so that anything that can happen in arbitrary order can happen in any of those orders, and it will still be a correct result. It doesn't matter if the child or the parent executes first. Either way, it'll still be correct. You need to make sure that you deal with the zombies. Don't have zombies just sitting around. You need to make sure that you, every time when the children die, you take care of them properly. You handle those signals correctly. And also, when you're running a foreground job, of course, your shell cannot be used to type in new commands until that foreground job is over. So you should think carefully about what the right way to make the shell not do anything more until that foreground job ends is. Okay, so let's go through some of the actual handout. If we can all see that. So I've untarred a copy of the handout over here. So this is what it sort of looks like. There's a lot of stuff. So what we initially give you is this tsh.c file. So this is your starter code, and we've defined a lot for you. Like I said, we've got all of this. We've got some structs defined for you. We've got the headers for a couple functions defined for you. And then we've got all of this is implemented way down here. This is all sort of stuff to manage the jobs. And then some of these are empty, and you'll have to fill them out. Stuff to manage jobs. So you should start by reading through that and understanding what we gave you, and understanding what parts you still have to implement, so that you know exactly what you're doing. But as you go along, what you'll do, so you write some part of your shell, and then you make. So this is the same as normal. And what that'll do is that gives you a whole bunch of additional new things. So it's compiled a bunch of programs, and these are sort of programs to test your shell out with. And then it's also compiled a couple things called run trace and sdriver. So these are what you'll be using to test as you go. And we also have a reference shell. So we've got your shell, the reference shell, and 2 test programs. So we can run the reference shell. This is actually really useful if you just want to sort of see, what should the shell do when I do a particular thing. You can run the reference shell, and it will, you should be matching it with yours. So maybe I'm going to run ls with the reference shell, and hey, look, it prints out everything in the directory. And then I can quit. If I run my own shell, then I can say, okay, what does mine do when I do bin ls? Well, that does absolutely nothing. Okay, that's great. So I know I have to update that. I better handle being able to run programs from my shell. What does it do when I quit? It does absolutely nothing. So far, the shell isn't very good. There's stuff that needs to be implemented. So how do I get out of it? Okay, I can use Control D to get out of it. At least that works. Control D. Okay. Control C was completely unhandled too. You can see it just printed out --C. Okay, so we want to sort of go through and figure out now, what should I do first? And you should do things in the order of the traces. So we've given you a bunch of trace files. They're numbered 0 through 24. And what a trace file is it has in it a list of commands that's going to be passed into your shell, and it's going to run it on your shell and run it on the reference shell and make sure that they did the same thing. This one is an empty list. These lines starting with pound signs are just comments. This one just says if you give your shell just an end of file, does it actually just stop running? Which at least this one does. But then you can work up more to sort of more complicated ones, and now it's going to start running programs and stuff, and it's going to make sure that sort of your program is able to run a job in the background. This one's going to run MySpin in the background. Okay, so how do we go about doing this? So as we're going, we'll want to be able to run a particular trace on our shell and make sure that it's working on it. So there's this program run trace. You can see the information on it with the -h flag. And all you need to do, put that up again. So run trace, we'll say, okay, let's run trace05.txt, and let's run on our shell tshell. So this is our shell. And what happens? Well, okay, looks like it just timed out. Okay, so my shell cannot run that one appropriately. But if I did run trace05, and gave it the reference shell, then it would print out this. So this is a way to actually run the trace files, see what the reference shell does, see what your shell does, and you'll want them to be the same. So you should work through the trace files. You should work through them in order, pretty much, because most of them depend on the previous ones working to be able to work themselves. They sort of add things that they're testing. Particularly, I think it's trace02. Yeah, trace02. You need to get trace02 working before you can get any of the other ones working, because all the ones 3 and after rely on trace2 being correct. But you can work through them with run trace, sort of trying it out on the reference shell and trying it out on your own, seeing how it happens. You've got a flag -v that'll give you even more information if you want more information about what's going on. So now this is sort of printing out what's happening to the job list and what's happening with signals. And so you can go through this on the reference shell. That's really useful if you're not sure why yours is not doing the right thing. You can see what the reference shell did when it traced through it, and then check if yours is exhibiting similar behavior. Maybe you can see that they differ in some spot, and that's why it's wrong. Okay, and then once you've used run trace and you see that you're passing some traces, you can use sdriver. So sdriver is then the actual grading script, and we can check sort of what it takes. It'll run it on all of the traces by default, and it'll run it 3 times by default. We can. I'm not going to run it on all the traces because it's just going to do a bunch of failing and complain a lot because my shell is not implemented yet. But we could run it on a particular trace. So we could use -t and then say, okay, I just want to run it on trace 5. We already know that one doesn't work, but it'll print out the fact that, okay, so what did mine do? What did the reference one do? What was the difference between them? And so the difference is that mine complained that it timed out, and the reference shell did not do the same thing. And then 0 out of 1. So run trace is the way that you do particular traces, and then once you've got those working, you can run sdriver to sort of check that that's just going to run them all. And then it is really actually a good idea to just sort of use the reference shell. You can actually have the reference shell print out additional information. So reference shell with -v will print out additional information as you go. So it's actually one of the best ways to start, even before you're passing traces, is to sort of just run a program in the reference shell that does whatever you want to do with your trace and sort of see the details of what the reference shell is doing, because you want to be doing the same thing. So, and then one important detail is that these process IDs, so every process has a process ID associated with it in the system. These are not unique. They're different every time. So here it was 22463, now it's 22494. Those will be different, and the grader, of course, will ignores the fact that the process IDs are different. Other than the process IDs, though, you should be exhibiting the same behavior as the reference shell. So, and then we can, when we edit our shell and we open up the file, we change it, then we can make again and compile the new version to try out our tools on it somewhat. So any questions about the programs for Shell Lab, how to run it, the stuff we talked about? Yeah. Yeah, you can use the stuff from the website. Yeah, that's all. Yeah, so if you, as long as it's included in the tar. So actually, I want to see. Yeah, so as long as it's included in the tar, it will be fine.
Do you have to be able to handle background and built-ins or built-ins background like
Yeah, so the built-ins you can't background. So we can run the reference, and if we do like quit and try to background it, oh, actually, okay, it does quit. Interesting. Let's get it to print out some more information and see what happens. So if we do quit and we try to background it, it just quits without printing out anything more. Okay, so maybe you do have to do that. So let's see. So there's another one, jobs. I guess we don't have any jobs. We did jobs, backgrounded. Okay, well, you can play around with the reference compiler and just match that. It's the best reference.
All right. Well, what I got from that is that I don't want to do this lab, the shell lab, because I don't think I'll learn much from it. I thought maybe I would, but they provide so much of the implementation for you that it's really about just implementing like 2 bits. From what I gathered, 2 major bits, and handling a bunch of signal stuff, which I have just done so much of that over the past 6 months that I don't want to do more of it. I don't think it'll be beneficial for me, so I'm going to skip the shell lab. Let's get into the next lecture, virtual memory concepts. We're at 12 o'clock, got about an hour, so I'll 2x this probably. How much is it? Let's just 1.25.
Welcome, good to see you as always. Today we're going to learn about an important concept in computer science called virtual memory. So consider a system that uses physical addressing, right? We've always, our idea about memory so far has been that it's a contiguous array of physical bytes that we can access just by giving an offset called an address. So in a system that uses physical addressing, the CPU executes, like, say, a move instruction, which generates an effective address, the physical address. And this address is actually the offset of a byte in main memory. So here the CPU has generated a physical address of 4, sends that address to the memory, and then the memory fetches the word from at that address and then sends it back to the CPU. Now, this is, in fact, the way that very simple microcontrollers work. But it's not the way most systems work, including your phones, your desktops, your servers. These systems instead virtualize this main memory. Now, the idea of virtualization is a very important one in computer science, and it expands it applies to a lot of areas of computer systems. Now, when you virtualize a resource, you present the user of that resource with some different kind of view of that resource. You present typically some kind of an abstraction or some kind of a different view of the resource. And you do it by interposing on accesses to that resource. So in all cases, there's some resource, and you want to virtualize it. And you do that by intercepting or interposing on the accesses to that resource. Okay. And then we saw this when we created wrapper functions for like malloc when I was showing you interpositioning. The same technique is used to virtualize a resource. And once you've intercepted that access, then you can deal with it any way you want. And so that's how you have sort of full power to change the view of that resource. Okay. So a good example, you saw this when we looked at disks. And physically, disk consists of cylinders, tracks, sectors, platters, surfaces. And to access a particular sector on one of those disks, you have to specify the cylinder and the track and the surface. Okay. But we saw that the view that disk controllers present is actually different. It's a virtualized view of the disk. And the controller instead presents to the kernel a view of the disk as a sequence of logical blocks. And it presents that view by intercepting the requests from the kernel for I/O and changing those logical block numbers that the kernel sends into the actual physical address. Okay, so that's a very important example of virtualization in a system. Now, the memory is a crucial resource in the system, and what we found is that it's useful to virtualize that memory resource. Okay, and the way this is done, you remember before we virtualized the disk by having the disk controller intercept request. In the case of the main memory resource, the requests are actually intercepted by a piece of hardware called the MMU, the Memory Management Unit. So the way this works is that the CPU executes an instruction. Say it's a move instruction that generates some effective address. So this is actually a virtual address. The CPU sends that address to the MMU, which goes through a process called address translation, which we'll study later today. And it converts that virtual address, in this case 4100, into a physical address, 4, which actually corresponds to the address of the data object that we want. Okay, so once the MMU translates the virtual address to a physical address, then the memory will return the word at that address. So this, you might wonder, why in the world would you want to do this? Well, it turns out there's all kinds of good reasons to virtualize the address space. And so before I can explain those to you, let me just define a few terms. So an address space is a set of addresses. Okay, so an address space is a set, not of data bytes, but of the addresses of those bytes. And a linear address space is an ordered set of contiguous non-negative integers. Okay, so just 0, 1, 2, 3, 4, 5, and so on. The virtual address space is a set of n equal 2 to the n virtual addresses. It's a linear address space. And the physical address space is a set of m equal to m physical addresses. Okay. And so typically, the virtual address space is usually much larger than the physical address space. Okay, the physical address space corresponds to the amount of DRAM that you actually have in the system. The virtual address space is the same for all processes running on that system. Okay. Now, why do we want to implement virtual memory? Why do this? Why do this level of indirection with the MMU? Well, there's really 3 big reasons. So the first is that virtual memory uses the DRAM as a cache for the actual data stored on disk. Okay, so you can think of virtual memory as a DRAM cache for data stored on the disk. And this allows us to use the memory much more efficiently, because we only need to cache items that are frequently used, right? Just the same idea that we learned when we talked about caches and locality. So that's one thing. We can use the memory much more efficiently by only using the portions of the virtual address space, by only actually storing the portions of the virtual address space in the physical memory. Okay. The second thing is it greatly simplifies memory management. So we saw every process has the same view, right? There's code code and data are always loaded at the same address. The stack is at the top of the user visible address space. So and every process has the same similar looking virtual address space, but in actuality, that the memory that corresponds to those addresses is actually scattered all over main memory. Right? Okay, so that's a really important benefit of virtual memory. And then finally, it allows us to protect accesses. So remember, we had a process. We saw that a process provides this separate address space that's protected from accesses by other processes. Okay, so virtual memory allows us to create these separate, protected, private address spaces. Okay, and so what we'll do today, we'll look in more detail at these 3 ideas, and then we'll go into the specifics of address translation. So I'm going to, for the first part of this lecture, we're going to talk about address translation just in kind of high-level terms, but then we'll go into the details at the end. You can see how it really works. Okay, so let's look at VM as a tool for caching. So conceptually, you can think of your virtual memory as a sequence of bytes stored on disk. Okay, and then the contents of that virtual memory stored on disk are cached in DRAM. Okay, so think of the DRAM as a cache for this array of contiguous bytes stored on the disk. And just like any cache, the data is broken up into blocks. Okay, and then we have so here we have and those blocks for virtual memory systems are called pages. They're typically much larger than the cache blocks that we studied. So it's 4K bytes typically instead of the 64 bytes like that we learned about when we studied cache memories. So this virtual memory, conceptually, you can think of it as being a sequence of pages stored on the disk, so-called virtual pages. And each of these pages we'll identify with a number. So here's virtual page 0, virtual page 1. And then a subset of those pages are stored in the physical memory, in the physical DRAM memory. And then there's some mapping function that tells us which pages have been cached. Okay, so in this case, I've just shown a snapshot where we have 3 virtual pages cached somewhere in DRAM. Okay, and there's no relation between the virtual page number and the physical page number that it's mapped to. Some of these pages are not cached, so they're still stored on disk. So in this case, VP2 is still stored on disk. And there's some pages which aren't even allocated, so they don't exist on the disk yet, is a way to think of that. Right? Because we really wouldn't want to store every single page in an address space that's size 2 to the 48th. We really wouldn't want to store all those on disk. So most of the address space is unallocated. So we can just think of this. So this DRAM is just a cache, but it has a much different organization than the cache memories we studied earlier. And the difference is driven by the enormous miss penalty when you go from, if you have a cache in DRAM, the miss penalty to fetch a data item from the disk is huge. Right? So the design of this virtual memory cache is totally driven by this enormous miss penalty. And so as a result, the blocks are larger. So remember, we talked about that the block size is kind of a trade-off between sort of being able to usefully amortize the cost of fetching that block versus sort of consuming too much of the scarce cache space. Right? So in this case, our cache memories were 64-byte blocks. Most virtual memory systems have like 4K byte blocks with an option to increase to 4 megabytes in the case of x86. And now this cache, another consequence of the enormous miss penalty is that you really want to have as large associativity as you can. You remember we saw with direct map caches that were subject to these conflict misses. And if you increase the associativity of the cache, you reduce the probability of those conflict misses. But you never completely eliminate them until you have a fully associative cache with just one set. Okay. So in a virtual memory cache, it's fully associative. There's one set, and each virtual page can go anywhere in the cache. Okay. So this requires a really complicated mapping function. Somehow we're going to have to keep track of where all these cached pages are. Right? And we can't really do a search. That would be way too inexpensive. So you remember when with a cache memory, the hardware actually did a search within the set, a parallel search to try to find a cache line. But with a software cache like this, that's not feasible. Right? So somehow we're going to have to remember where these cached blocks are in this very large set. And again, because it's so expensive, if you make a mistake, when you're trying to identify a victim page, if you make a mistake and you evict a page that then is referenced again in the near future, you pay a big price for it. Okay? So virtual memory caches have much more sophisticated replacement algorithms than like simple LRU that we saw with cache memories. Now, these replacement algorithms are outside of the scope of this course. You'll learn about them when you take OS. But because it's in software, we can afford to do very expensive replacement algorithms. And we can take a relatively long time to execute the code for those algorithms, because any time we spend figuring out a victim block will be much less than the cost of making a mistake and paying the access time, the miss penalty to disk. And then also as a result, virtual memory systems never use write-through, just because it takes too long. Right? So they always use write-back, and they try to defer writing anything back to the disk as long as possible. All right, now how do we keep track? Somehow we have to keep track of this complicated cache in DRAM. And the data structure that keeps track of the location of the virtual pages in memory is called the page table. Now, a page table is just a data structure in memory that the kernel maintains as part of each process context. Okay, so every process has its own page table. And it's just it's an array of so-called page table entries, or PTEs, where PTE k contains the physical address of physical page k in DRAM. Okay. So here's how it works. There's this page table in DRAM. There's virtual pages stored on disk. And then there's virtual pages stored in various physical pages in DRAM. And then the page table keeps track of where those are stored. So here we have a case. This PTE1 corresponds to virtual page 1. And in this case, it says that virtual page 1 is mapped into physical page 0. Virtual page 2 is mapped into physical page 1, and so on. Okay. Now, some of these, the pages that aren't in memory are stored on disk, the allocated pages. And so for those pages, the page table entry contains a pointer to the location of that page on disk. So think of it as a logical block number where that page can be found on the disk. And then some of the pages are not allocated, so there's a null entry in the page table. Now a page hit, so this is just a cache, right? So we have hits and misses. So a page hit occurs when there's a reference to a word in the virtual address space that's contained in a page that's cached in the DRAM. Okay. So let's say that we have, the CPU executes this move instruction. It generates a virtual address. The MMU looks up in the page table, and let's say this virtual address is somewhere within virtual page 2. Okay, so the MMU looks up the page table entry, number 2, and it extracts the physical address of that virtual page 2. Okay, so that's a hit. So in this case, the page is in memory. It's cached in memory, and so we have a hit. And now the memory can return that physical address to the MMU. Okay. Now, a miss is a reference to a word that's not cached in physical memory. So in this case, virtual page 0, 1, 2, 3 is not cached in DRAM. It's stored on the disk. So now that triggers an exception, okay, a page fault exception in the hardware. The hardware triggers the exception, and that causes a transfer of control to a chunk of code in the kernel called the page fault handler, which then selects a victim to be evicted, in this case, virtual page 4. And it fetches virtual page 3 from the disk, loads it up into memory, and then changes and then updates this page table entry to reflect the fact that virtual page 4 is now stored on disk. And if virtual page 4 had been modified at any time, it would have to write the contents of that to disk as well. So once the handler has copied virtual page 3 into memory, the instruction that caused the page fault now can be re-executed. Okay, so when the page fault handler in the kernel returns, it returns to the faulting instruction, which then re-executes. And now that page is, when the MMU checks that the PTE corresponding to that page, it finds that it's indeed cached. So now the instruction can continue, and we can fetch that whatever word at that virtual address from the DRAM. Okay, now we can allocate a new page of memory. So in this example, virtual page 0, 1, 2, 3, 4, 5 is not allocated. So if you need to, let's say you do malloc of a very large chunk of virtual address space, if one of those pages hasn't been allocated yet, then the kernel actually, or the malloc function actually has to allocate that memory by calling a function called sbreak. Okay, and then what sbreak does is actually allocates this page and records where it's loaded. Now it would probably actually put it up into no, I guess it wouldn't actually show up in the DRAM cache until that page was touched. Okay, so just allocating space just changes this page table entry, and then when that page is actually touched, then it'll be brought into the cache. So I don't know about you, but the first time I learned about this, I was pretty appalled. It just seemed like the most inefficient, terrible idea, right? How in the world can you afford to, on every single instruction that uses memory, do all this copying back and forth and looking up in tables? And it just seems like an awful idea. But once again, locality saves us, okay? And it actually works because programs have locality, okay? And it's actually fairly efficient. And the reason is that at any point in time, programs tend to access a set of pages called the working set, okay, just by locality, right? By temporal locality, by the principle of temporal locality and spatial locality, you tend to sort of reuse the same things, reuse nearby things, okay? And so if that working set is less than the main memory size, then all of the pages in the current working set will fit in memory, and then things will be great, okay? But if the sum of the working set sizes for every process, right, our system's running multiple processes, if it exceeds the main memory size, then you have this meltdown where processes are thrashing each other and causing pages to be copied back and forth. So no process ever gets its working set fully into memory. Okay, and we'll look at a technique when we look at address translation. We'll look at a little hardware cache called a translation look-aside buffer that further exploits the locality property of programs. Okay, so that's virtual memory as a tool for caching. It's also a tool for memory management, and it greatly simplifies all kinds of aspects of memory management for the kernel. So the key idea is that each process has its own virtual address space. The kernel implements this by giving each process its own separate page table in the context of that process. So it's just a data structure in the kernel that the kernel keeps for that process. And the page table for each process maps the virtual address space for that process. Now, what's interesting, so you have these pages, contiguous pages in the virtual address space, can be mapped anywhere in the DRAM, in the physical address space. So, and they can be scattered all over the place. And different virtual pages in different processes can be mapped to different physical pages. So here we have virtual page 1, which is mapped to physical page 2 in process 1. But in process 2, virtual page 1 is mapped to physical page 8. Okay, so in this way, we can present a view to the programmer and to the tools that each process has a very similar address space, virtual address space, same size address space, code and data start at the same place. But then the actual pages that process used can be scattered in memory. Okay. And then it gives us the most efficient way to use the memory. Okay. If we didn't have this mechanism, think about how would you keep track? Let's say you had 50 processes running on the machine at any point in time. How in the world would you keep track of where all of the data those processes were using? Well, one technique that you could imagine, in fact, it was used in the bad old days before virtual memory. One thing you can imagine is that just give every process its own chunk of the physical address space. Just take your physical address space, partition it, and then each process loads and runs in its own part of the address space. Well, this has all kinds of problems, right? I mean, you could, what do you do if you add a process? So you really can't partition the address space. You really have to sort of say, well, each process gets some little chunk, and I'm going to reserve some of the address space in case there's new processes that need memory. Another problem is that now you have to write your programs. You can't just link your program ahead of time because it has to be relocated when it's loaded, right? Because a process, you don't know where in the memory it's going to go. It's going to get some chunk. So you have to either relocate all the references, the references to global symbols when it's actually loaded, Or you have to create a system where all of the instructions are relative. So there's no absolute addresses. All addresses are relative to, say, the start of the program, something like that. So anyway, all of these things are just terribly complicated, and they're all solved beautifully by virtual memory. So each virtual page can be mapped to any physical page, so that really helps simplify things. And even at different times, the same virtual page can be stored in different physical pages at different times. Right? So if a page, for a while, it might be cached in one physical page, then it gets swapped out, and the next time it's referenced, it can get cached in a different physical page if it's no longer available. Right? So it provides sort of the most flexible scheduling freedom in the way that we manage the memory. And it also provides this really neat capability where you can map virtual pages to the same physical page. So this is a very simple, straightforward way for multiple processes to share certain code or data. Okay? And what you do is the page table entry in these different processes just points to the same physical page. So in this case, virtual page 2 points to physical page 6 in each of the page tables for process 1 and process 2. So this is how shared libraries are implemented. Right? So libc is the same code for every process running on the system. So libc just needs to be loaded once into physical memory, and then processes that want to access functions and data in libc just map the pages in their virtual address space to the physical pages where libc is actually loaded. Okay, so now there's only one copy of libc everywhere in the system, but every process thinks it's got its own copy. Now this virtual memory using virtual memory to help simplify memory management greatly simplifies linking and loading. Okay, for the reasons I mentioned before, linkers now can assume that every program is going to be loaded at exactly the same place. So the linker knows ahead of time where everything's going to be. Right? And then it can relocate all those references accordingly. Now, it really makes loading simple. So execve, the loader, if you want to load a program now, execve looks at the ELF binary, the executable binary. Okay? It sees it identifies how big the code and the data sections in that binary are. It allocates virtual memory starting at a fixed address for the code and data. Okay? It creates PTEs for them and marks each of them as invalid. Okay, so each PTE contains a valid mapping. So each PTE that's mapped to code and data contains a valid physical page number. But then it does this trick of setting the valid bit to 0. So when the MMU encounters a PTE whose valid bit is 0, it triggers a page fault. Right? It looks as though that page has not been initialized yet. So it's kind of a trick. Right? And then that triggers a page fault to the kernel. And then the kernel will then can then copy that page into physical memory. Okay, so the loading, actually programs and data they're not loaded, they're not just like copied into memory. It happens as a result of page faults. It happens as a result of misses. And it's deferred until a byte in that page is accessed. Okay, so this is called demand paging. Okay, but it's really just like any of the other caches we've looked at, right? You don't load a block into the cache until a word within that block is accessed. Okay. So loading's actually is a very efficient mechanism, right? Because you may have a program that contains a huge array, a large array, but you're only accessing a portion of that array. So that entire array won't actually be allocated. The pages will only come into DRAM when a word within that page is touched. So if you're only accessing a portion of this extremely large array, only the data that you access gets loaded and used. Right? So it's a very, very smart mechanism and extremely helpful for allowing us to use this precious memory resource. Okay, so the third motivation for virtual memory is that it helps us protect portions of memory. So you recall that our processes, portions of our virtual address space are read-only, like the code section. Okay, and there are other portions of the address space that can only be executed by the kernel. Okay, so on systems like x86-64, it's a 64-bit system, so the pointers and addresses are 64 bits. But in actuality, the real virtual address space is 48 bits. Okay, so it's 2 to the 48th, and then the higher order bits after bit 48 are either all zeros or all ones. Okay, so that's sort of Intel's rule. Okay, and so the addresses where the high order bits are all ones are reserved for the kernel's code and the kernel's data. Okay, the addresses where all the bits are 0 are reserved for user code. Okay, so any address that contains all ones in those high order bits is by definition either code or data in the kernel. And so you can add bits to the PTE that specify whether certain virtual pages can be accessed by user code or if they have to be accessed by the kernel. So the so-called supervisor mode. And you can also add bits that control whether that page can be read, written, or executed. Okay, so this execute bit is new with x86-64. It didn't exist in 32-bit x86 systems. And this is the technique that's used now to try to prevent against attack lab code injection style attacks, because it makes it impossible. If this bit is set, you can't load instructions from any byte within that page. So in fact, it was this the introduction of this execute bit that sort of led to things like return-oriented programming attacks, like you did in your attack lab. Okay, so this by just the simple technique of adding bits to the PTE, we provide an automatic way to protect different parts of our virtual address space from unauthorized accesses. And then the MMU actually checks these bits on each access, and if there's a problem, if you're trying to do a write and the write bit's not enabled, then it throws an exception, which then the kernel deals with. Okay, so far I've been talking about address translation in kind of high level terms. So let's get down to details and see how it really works. Okay, so we're given a virtual address of n elements, a physical address of m elements. Like I said before, n is usually larger than m, but it doesn't have to be. Okay, there's no reason m could be much larger than n, and it's typically not, but it could be. And so given these two address spaces, we have a map function that maps from v to p with an optional empty set, or an additional empty set. And so for virtual address A, map A is equal to A prime if the data at virtual address A is at physical address A prime. Okay, so I mean that's just it's just a little more formal way to say what we've been talking about before with our diagrams. And then map A is the empty set if the data at virtual address A is not in physical memory. Okay, so just for a summary, I'm going to put up a list of all the symbols we're going to be using in address translation, but this is just for a summary. This is just for reference if you're using the slides later on. Okay, so here's how address translation with a page table works. So we're given some virtual address that consists of n bits. And we have blocks that consist of whose size can be represented with p bits. Okay. So think about this now. So this is very similar to what we looked at when we did caching, the address bits for a cache. So these first p bits correspond to the page offset. So this is analogous to the blocks offsets that we saw with caches. And then the remaining bits correspond to the virtual page number. So remember, this is fully associative, right? So there's only one set. So in a fully associative cache, everything after the block offset is tagged. So think of this as like a tag. This is what uniquely identifies this block. Okay. And in virtual memory parlance, we refer to it as a virtual page number. Now, the page table, the beginning of the page table is pointed to by this page table base register. On Intel systems, it's called CR3, control register 3. But this register contains the physical address of the page table in memory. Okay. The beginning of that. And so when the CPU presents a virtual address to the MMU, it takes the virtual page number and uses that as an index into the page table. Okay. And that identifies a page table entry which contains, if this is mapped into memory, it contains the physical address of the corresponding physical page. Okay. So the whole purpose of address translation is to come up, you're given a virtual address, and you want to come up with a corresponding physical address. Okay. So the physical address, the physical page number portion of the physical address comes out of the page table entry. And this is interesting. The physical page offset portion of the physical address comes out of the virtual page offset, and those bits are identical. Okay, so now you should convince yourself that this is true, right? The offset in a virtual block is going to be the same as the offset in a physical block. Right? They're the same size blocks. And you can also see why this virtual page number identifies the page number in the page table. So imagine a virtual address that's all zeros. Okay, all zeros. So it's virtual address 0. And now that will have a virtual page number of 0, and the byte at that address will be at offset 0. Okay. Now increment by 1, virtual address 1. So that'll be at an offset of 1, and it'll be in the same virtual page of 0. Right? Now keep incrementing until all of the bits in the virtual page offset are 1s, and the virtual page number is 0. Okay, so this is the last byte in that virtual page 0. Now increment one more time. The 1 bit carries over to the virtual page number, so now we go to the next virtual page, and it's at an offset of 0. Okay, so can you see it's sort of obvious when you think about it like that. Why we can just take these bits after the virtual page offset and use them to uniquely identify what virtual page we're working with. Okay, So let's see how a hit works in this system in more detail. So our CPU sends a virtual address to the MMU as a result of executing a move instruction or call or return or any kind of control transfer. The MMU looks up the PTE, so it fetches the PTE from the page table stored in memory. So this is actually going off the chip onto memory, into this PTE stored in memory. It fetches the PTE, extracts and uses that PTE to construct the physical address. Okay, and then it sends that physical address to the cache and memory system, which eventually results in the data being returned back to the CPU. Okay, so even for a hit, we still have memory references, right? Because we have to fetch that page table entry. Now, a miss is, in this parlance, is called a page fault. So in this case, the same thing happens as before, that the CPU sends the virtual address to the MMU. The MMU fetches the PTE from memory. But then when the MMU looks at the PTE, it sees that there's either an invalid valid bit or a zero valid bit, or it's indicated that the data is stored on disk. And so in that case, the MMU triggers a page fault exception, which transfers control to this page fault handler. The handler identifies a victim, and if it's been modified, copies it out to disk. Then it fetches a new page from disk into memory and up through the cache hierarchy. Okay, and then it causes that then the handler returns to the process, and when a handler for a fault returns, it causes the faulting instruction to re-execute. So now the move instruction that faulted is re-executes, but this time there's a page hit. Now you may be interested in how the cache is integrated into all of this. So the MMU fetches page table entries, so it passes page table addresses to the cache. If those miss, those go to memory. The memory returns those page table entries to the cache, and then ultimately to the MMU. The MMU constructs that physical address, and then it sends that physical address to the cache. Right? So with caching, the way we've been caching is done using physical addresses. Okay. In this case, it's also possible to construct caches that work with virtual addresses. But yes. Yeah, so we'll get into that. Okay, so the question is how is the virtual address space implemented on disk? And what it actually does, it does a much more efficient thing than the sort of abstract model that I described. So most pages, there's an option when you allocate a new virtual memory page, you can allocate it so that it's all zeros. Okay, so there's a special, you can say I want to allocate a page of all zeros. In that case, that page doesn't need to ever get stored on disk. Right? It's just the memory. It's as though it was created on disk and then loaded into memory. So those pages that are all zeros don't exist on disk. When pages are modified, it's a little more. Pages can be mapped to particular files. For example, when we load an ELF binary, the pages that correspond to the code are actually mapped to the bytes in the binary that contain the code. So that when you miss on that page, it brings in those code pages. Okay, so pages can be mapped to user-level files on disk, or not. They can be anonymous and not mapped. So if they're mapped to user-level files and you write to a page, then it'll get written back to the page that it's mapped to. If it's not mapped to any page, it's stored in this area called the swap area, or the swap file. Okay. Yes?
When you load a page from disk into memory, does the portion of that page get loaded from memory to cache into like the L1 layer?
Oh yeah, so the question is when you load a page from disk into memory, does it also get cached in the cache memory hierarchy? And the answer is yes. So if you load an entire page, that page will be broken up into blocks, 64-byte blocks, and loaded into the cache. So everything that you fetch from the cache goes through from the memory goes through the cache hierarchy. Okay, so I claim that virtual memory works because of locality, and that's true. But if we still had to fetch, if every time we had a miss, we still had to go to memory, it would be too inefficient. Okay, so the MMU speeds up this translation process by caching page table entries in a hardware cache within the MMU called the translation look-aside buffer, or TLB. So the TLB is a hardware cache that caches PTEs, page table entries. And it contains a cache of the most recently, it's just like any other cache. So it contains a cache of the most recently used page table entries. And so the MMU, remember the unique part of a virtual address that defines a virtual page is the virtual page number bits. Okay, so the TLB uses the VPN portion of the virtual address to access it. And so that just like any other set, it has a set of set index bits, which are just determined by how many entries or how many sets the TLB has. And it has a tag for the remaining bits to disambiguate any to disambiguate any cache lines or PTEs that map to the same set. Okay, so the VPN or the TLB index maps to this particular set, and then it uses the TLB uses the TLBT bits to disambiguate and determine if the PTE that it's looking for is really stored in the cache. Okay, so the way this works is CPU generates a virtual address. It goes through the MMU. The MMU, instead of looking in memory and directly going to the page table entry, it first asks the TLB if it has that. It sends it the VPN and says, do you have this virtual page, the PTE for this virtual page? And if it does, the TLB returns a hit, and it returns that page table entry, which the MMU can then use to construct the physical address to send to the cache and memory system. Eventually, that results in the data being sent back. Now, when you have a miss, then there's this one, the MMU checks with the TLB for the PTE. It misses, so then the MMU has to go to memory, just like before. Okay, so this is, and then everything is the same. The memory returns the PTE to the MMU, which stashes it in the TLB. And just like before, if there's no room in the, if a PTE has been modified, then it has to be written back out. Okay, just like any other cache. And eventually, the MMU uses that to construct a physical address, and then the data gets sent back. Okay, if you've been paying attention, unlike a couple people, if you've been paying attention, you're going to be very concerned about the size of these page tables. Right? I mean, we've got 4K bytes. Suppose we have 4K byte pages, and our effective address space is 48 bits, like it is with an x86 64 system. And we have an 8-byte page table entry. We'd need a page table of 512 gigabytes. Okay, 2 to the address space, 2 to the 48 bytes, divided by 2 to the 12 bytes per page. Okay, so that's the number of page table entries that we need. And then the size of each page table entry is 8 bytes. So we'd need almost a terabyte of DRAM just to hold the page table. Right? So that obviously is not going to work. And it's obviously not how their page tables are really implemented. So the solution is to use a hierarchy of page tables. So if we have a 2-level page table, there's a first level page table called the level 1 table, which is always in memory. Okay, it's never paged out. And then there's a sequence of level 2 page tables, and they're all the same size, right? And the first level 1 table points to the beginning of the first level 2 table. So it contains a physical address that points to the base. The second level 1 table points to the second level 2 table, and so on. Okay? So if we have this kind of system, remember, most of the virtual address space is unused. Right? So if we have this kind of system, we can avoid creating many unnecessary page tables. Okay? So imagine if we have a 2-level hierarchy. So let's look at our virtual address space in this example. And what I've allocated 2K pages for code and data for this program. And then there's 6K unallocated pages. And then the stack, then there's a page that's allocated for the stack. I'm sorry, there's 1,024 pages allocated for the stack, most of which are, I'm sorry, there's a region of memory that's the size of 1,024 pages, but most of them are unallocated, and I've only allocated one for the top of the stack. Okay? So given this layout for my process, I only need 3 level 2 page tables. Okay, the first page table covers this region of my code and data, the first 1,024 pages. The next page table covers the remaining 1,024 pages. Okay, so these two level 2 page tables cover all of the code and data. Okay. And similarly, what I need for my stack, I just need 1 page table, and it only has one valid PTE, it's the very last one. Okay, and then I have a single level 1 table that points to the 3 level 2 tables. Okay, so with 4 page tables, I've covered the entire virtual address space. Now, the way that the MMU uses these multiple page tables to do address translation is as follows. We have the virtual page offset, which consists of the first P bits. And then the VPN, the remaining bits, the VPN, for a K-level page table are broken up into K sub-VPNs. Okay. And each is the same size. And so now in this system, the upper VPN 1, which consists of the uppermost bits of the VPN, are an offset into the level 1 table, which is, as before, is pointed to by the page table base register. Okay, so VP1 is the index into the level 1 page table. Remember, the level 1 page table points to the address of the level 2, or an entry, a PTE in the level 1 table, points to the address of some level 2 page table, or it contains the address of some level 2 page table. So that points to the base of this level 2 page table, and then the VPN 2 bits are used as an index into that level 2 table, right, and so on. Okay. So eventually, you get at a PTE in the level k-1 table points to the beginning of the level k page table, and VPNK points to an offset within that table, which finally contains the physical address of the page that we want to access. Okay, and then that physical address is used to form the PPN portion of the physical address. And just like before, the virtual page offset is just copied directly unchanged to the physical page offset. So is that clear to everybody? Yes, question?
So does that mean that the number of levels will always be a power of 2, and it cannot be more than 6 levels?
Let's see, is it always a power of 2? Yes, at least. And it's defined by the architecture. So for Intel, it's a 4-level system. Now, why would it be, and then will it always be less than 6?
Right, because 2 that's different.
Oh, if it's a 64-bit system, yeah. Yeah, there's only, the block size is fixed, right? So there's 12 bits here. 2 to the 12th is 4K. So the remaining, you actually have 48 bits to play with. Right? So the remaining 48 bits that's right. So if it was 4, if it was 8, it would be 6. So you're right. In this scheme, it could be at most 6. Turns out in practice, it's set at 4. And there was a question over here?
Oh, yeah, I don't understand what the play tree is. Like, how does it save you any space as compared to just having the one page table?
Have it like this multi-level system?
Right.
Oh, okay. So the question is, yeah, the question is, how does it save you space? So the reason it saves you space is, you go back to this other figure. Maybe I didn't explain this well enough. So you see this. So let's say we wanted to map this virtual address space with a single page table. We would need a PTE for every page within that address, whether it was used or not. Okay, it goes back. If we had a 48-bit address space, we'd need a page table entry for each virtual page in that address space. Okay, whether that page was used or not. So I mean, think about it. 2 to the 48th is several exabytes. We'd need a page table that had an entry for each virtual page in that 2 to the 48th-bit address space. And most of those pages, by far, the vast majority, would never, ever be used. Okay, so that's where the waste comes in. Okay, so here, with a multi-level page system, with this multi-level scheme, you only need to generate, in this case, these level 2, if it's a 2-level system, you only need to generate level 2 page tables, enough level 2 pages to cover the portion of the virtual address space that you're actually using. Okay, and that portion of the virtual address space that you're not using, like this gap right here, there's no need to have a page table. Is that clear? That's a really good, important question, but you look unconvinced.
Would you ever have to, like, so it says like PTE 2 to 7 and all, would you ever have to like allocate one of those if you need to make another like table?
Well, yeah, you still need a page table that has, let's see, in this case, there's 4K byte pages, 4 byte PTEs, so there's 1K, you have 1K PTEs in this. So you still need a level 1 page table that has 1K PTEs. But those are only 8 bytes, right? I mean, so you still need to have space because you don't know. You're not sure which region of the address space you're going to need to cover. Okay, and it's the same thing for here. In this case, in these first 2 PTs, these first 2 level 2 page tables, their portion of the address space was actually all being used. Right? So each one of these PTEs at level 2 had to be initialized and used. Right? But in this portion of the address space that contained the stack, this third level 2 page table has most of its PTEs are null. You still have to allocate space for them, but they're null. Okay, that's a really good question. It's important. I hope that's clear. Any other questions? Before we go on? Sorry. Oh, okay, question.
So when you're indexing, then say you have this 64-bit address, each level of the page entry, or each level of the page table, it just looks at part of the address, so it indexes by the first 4 bytes and then... Exactly.
Just like here, the MMU member is doing all of this. This is all hardware logic. So the number of page tables levels is defined by the architecture. Okay. So the MMU takes the virtual address that's presented to it, and it uses a subset of those bits to access each page table. Okay. So it's just like, did I answer your question? Okay. So it's just like before. The level K, VPN K, is used to compute an index into the level K page table. Yes.
Why are the indices arranged right to left on the diagram? Why does it start at 0 and then go n minus 1?
Okay, the question is, why are the indices arranged right to left? On which diagram?
So on this diagram, you have 0 at the top right.
Oh, these are the bits. This is the least significant bit. It's always bit 0. Yeah, that's a good question. So the question was, why do in this diagram, why are these bits labeled right to left starting at 0? And the answer is that we're indicating the bit position. So 0 is the least significant bit, and n minus 1 is the most significant bit. Yes, question?
So what's the overhead when we increasing the number of levels that we use for the different levels?
Yeah, so the question is, what's the overhead involved in these, when you have these multiple levels? Now, are you talking about overhead to?
Increasing, for example, right now we use 4, how about we use 6 for the current process?
Yeah, well, so there's clearly, if you don't get TLB hits, it would be a lot of overhead, because you would be fetching PTEs from multiple page tables from memory. So that, but because of locality, the chances are almost, the chances this level 1 table covers the entire address space. So it's always going to be in the TLB. These level 2 tables are covering a huge swath of the address space. So chances are they're going to be in the TLB too. Right? So as long as your program has reasonable locality, most of these lookups are going to hit in the TLB. Okay, so it turns out that the overhead with reasonably written programs it's negligible. But it's a very important consideration. And maybe that speaks against increasing. At some point, if you had too many page tables, you might increase the probability of misses in the TLB. So it's probably something they very carefully considered. Okay, any other questions? Yeah.
So if we use segmentation plus paging, so is the address in page table the segmented linear address or real physical address?
Oh boy. The question was, how does segmentation fit into this? And we're not going to go there. Sorry. So in earlier Intel systems, such as actually the first Intel system I programmed was a 286. Was it 286? No, it was the 8086. Anyway, earlier Intel systems had 16-bit addresses, which is tiny, right? It's only 2 to the 16th for your address space. And so as a hack, to try to increase the effective size of this address space, they introduced the notion of segmentation. And so there were 4-bit, there were registers, segment registers that contained 4 bits that could be applied to the address. So an address was the combination of the segment. No, it was more than. Yeah, the segment formed, the address then was a combination of the segment bits plus the address. So you could use the segment bits to create an offset. So it was effectively a 2 to the 20-bit address space. But you could only access it in 2 to the 16th chunks, right? So the segment would determine an offset into this 20-bit address space, and then from that you could address 16 bits. So it was this very unsatisfying, devilishly hard to program thing because you can only access 16-bit chunks at a time. So anyway, we're not going to. A few years later, they came to their senses and just created a real virtual memory system with linear address spaces. So. But really, they're yeah, I don't know. We're just I'm not even sure if they do address translation on those actually. So I'm not sure, but you really don't want to go there.
So that probably doesn't exist anymore?
Oh, it does. It does. So the question is, it doesn't exist anymore. Everything, Intel's been incredibly good about maintaining backward compatibility. So that stuff's all in there. But there's a mode bit when you boot your system up. You set a bit that says, I want a linear address space. Okay. Any other question?
So VPN1 points to level 1. That points to level 2. So why do we care about the VPN3 points to level 2?
Oh no, VPN2 is the offset. Okay, so the question is, why do we care about VPN2 since it points to the level 2 table? So what gives you the beginning of the level 2 table is the PTE entry in the level 1 table. Okay, so the level 1 table points to the beginning of that level 2 table, and VPN2 gives you the offset into that level 2 table. So it finds the address by taking the base address and then VPN2 times the PTE size. So. Okay, good. Any other questions? Okay, well that'll do it for today. Next week, or on Thursday, we'll look at how virtual memory is implemented in real systems and in Linux.
Okay, lots of interesting stuff there that I wasn't familiar with. And this is I unplugged my headphones. Yeah, lots of interesting stuff there that I wasn't familiar with, which is why I wanted to actually read the text on this. And to be entirely honest, I kind of dozed off a little bit on that lecture. So it seems like he got to 9.5, section 9.5. So I'm going to go ahead and do the reading on that before I watch the next lecture. And I might even rewatch this lecture because, like I said, I kind of dozed off a little bit. Something about his, like, the way he talked was just, like, very soothing. Okay, let's put this at 12:45. Bam. So that finishes 2 hours. And I'm going to take a lunch break here. And I need to run to the grocery store to do that. So it might take me a little while to get lunch and cardio done this afternoon. But I'm going to go ahead and do that. And then this afternoon, I'm going to pick up, and we have, what, about 2.5 hours of reading on virtual memory that I'm going to do. And then this evening, I'm probably just going to play video games because, yeah, I kind of just want to do that. So I am very, very ahead on this course, and I'm cutting content that is a review for me. So if we go back to my CSAPP repo, or actually no, it'd be a learn log. We're at the end of the first week of April, and we're almost done with this book. We have virtual memory, and then a bunch of lectures basically to do, and maybe 1 or 2 labs left. So I'm thinking we'll definitely be finished by the second week of April, which means we're at least 2 weeks ahead on this this project. So yeah, I'm going to take a break then, and I will be back in about a little under 2 hours to continue reading about virtual memory. Cool. All right, see ya. Bye.